much more coherent, because if all particles change color in the same time, that means, of course, that the molecules can communicate. In a sense, I like to say that matter at equilibrium is blind, and far from equilibrium it begins to see. Therefore, you see, matter has new properties outside equilibrium. And therefore, we cannot say, oh, non-equilibrium, flow of time, that's all approximations to classical. No, it's not true. Matter is much more active, has different properties once you are in non-equilibrium situation, has new coherence. Really, it is then that you can speak about a system, that all the particles are working together, and the structure of the system inside becomes different from the structure outside. For example, when you take the Bénard instability, then once the Bénard flow begins, 2 points are no more equivalent. Euclidean geometry symmetries are broken, because when you go from one point to another, one point may be the point where there's a current going up, another point where the current is going down, and so on. So essentially, we see there the appearance of self-organization. Why self-organization? Because far from equilibrium, there are in general many possibilities. The equations are nonlinear, and you have generally many solutions compatible with the same boundary conditions in the system. Therefore, you come curiously to a situation which is opposite of the situation which mathematicians, physicists were so proud before. They said once the boundary condition or initial conditions both are given, there's only one solution. But here, there are many solutions. And small fluctuations lead to the system to one solution or the other. Therefore, we see on the macroscopic level two basic properties. We see on the macroscopic level irreversibility as a constructive element, and we see the role of probabilities. Because once you have bifurcation, appearance of new branches, you can no more speak about deterministic trajectories. Because you need a probability calculus to calculate, because the particle can go, the system can go either to one branch, either to the other. So we have two elements which are coupled, irreversibility and probability. My point of view has always been, for many years, that irreversibility needs an extension of the basic laws. Now, what can we mean by extension of the basic laws? And here comes a very important element which comes from the work of Poincaré at the end of last century, the work of Kolmogorov and all the Russian schools, Sinai and so on, in this century. And that is the role of instability. In other words, before the work of Poincaré, we saw that all dynamical systems are alike, not alike in complexity. Of course, we know very well it's much easier to calculate the two-body motion than the three-body motion. But after all, that may be simply a question of patience, of time which you want to devote to the problem. But since Poincaré and Kolmogorov and the later people, we know that there are stable systems and unstable systems, and that they have quite different properties. Now, the simplest example of a stable system, unstable system, are chaotic systems. And chaotic systems are systems in which neighboring trajectories diverge exponentially. And that is called the Lyapunov exponent. Now, therefore, let us ask, what are the laws of nature for chaotic systems? First of all, we have the fact that trajectories are idealizations for chaotic systems, because, as I said, neighboring trajectories diverge. Now, in fact, we can never prepare a point. We prepare always small regions. Therefore, we have in these small regions trajectories which go in all kinds of directions. Therefore, after some time, we shall no more be able to follow the trajectory. The uncertainty is increasing more and more. But that has been considered by many people as a more practical question. In other words, trajectories become uncomputable for chaotic systems. But from the fundamental point of view, there would be no difference. But I think the work done over the last years, and I'm very proud to say in which my group has participated very actively, is to go beyond this negative statement that we can only follow trajectories for a given time, that we have disorder, that chaos means that we cannot follow what will happen and so on. And that comes from the analysis what happens no more to single trajectories, but to probabilities. A probability is like you could look on an ensemble, and not only on one trajectory, but an ensemble of trajectories. Now, what has been proved, of course I shall not try to prove it in this interview, is that if you consider continuous probability distribution, this continuous probability distribution for simple chaotic systems, and I have in mind here especially what's called chaotic maps, in which time is acting every second, that's the simplest example, then you can predict the evolution of the probability. You can show how it will go to some limiting value, for example, equilibrium. And you can even predict the time scales. So you come to a completely new view of a law of nature. Because, in a sense, to obtain this law, you have to introduce probability as an initial condition. Generally, probability was considered as an expression of ignorance, as an expression of lack of knowledge. And here we need probability to obtain the evolution of the physical system on the level of probabilities, evidently. But that means, in a sense, that our initial condition is no more a point, but a small region. Therefore, we have a non-local description. And this non-local description is giving us more information, and especially the time scales includes a reversibility, which the local information could not. Chaotic systems with exponential separating trajectories are, in fact, a rather exceptional situation. Then how it happens that instability is so important? And that comes from another type of instability, which I would like to call Poincaré instability or Poincaré catastrophe. Poincaré, at the end of last century, asked a very important question. As you know, in the energy of a dynamical system, you have a potential energy and a kinetic energy. The kinetic energy of the particles, let's say, and some gravitational energy of interaction or whatever kind of energy of interaction. And I simplify a little, of course. Poincaré essentially asks the question, can I, through some clever